CVPR 24 Part 3. I'm discussing two papers in this episode. They're both presented by Sanja Fiedler. She is at NVIDIA and also professor at Toronto. The first paper is about grounding images with an LLM feedback. So you have an image, a crowded image. Let's say you're building a simulator and or even a real driving data set for autonomous vehicles, and you have lots of objects in an image. You're at a crossing in Manhattan, or you're somewhere where there's a lot of stuff, people, all that kind of stuff. So what you need is you need a better segmentation of the image. Now, I think auto-labeling has gone a long way since Karpati spoke about this 5-6 years ago. And I think we're at a point where we're pretty good at auto-labeling, but the segmentation part hasn't been solved to the satisfaction of production level models. And this is what Sanja was discussing. So in this case, she's introducing two interesting concepts. One is to have an LLM decide, okay, let me rephrase that. There's two interesting approaches in this paper. One is to use an LLM for auto-labeling, and the other is to have an iterative approach where the LLM is a discriminator to the vision language model, and through sort of a chain of thought type reasoning process improves its own improves the performance of the VLM. And the concept here, the idea comes from the human actually. When you write a piece, let's say an essay, you are then rereading it and fixing your mistakes. So the same brain that produces something can also fix something. This is the same idea, which I find unbelievably fascinating. So that in itself opens up a lot of philosophical conversation. Why is that even possible? The second paper is also, it's really very important. I think all the work that NVIDIA is doing towards simulation, in my opinion, is paving the way, paving the road for robotics. And I think Jensen and his team around Sanja and everybody else there are really doing phenomenal work. And it's just, you can't underestimate their foresight, the same way they saw CUDA 20 years ago as the tool for a $1 trillion company, the same way they're gonna, I think, do this again with simulation. So what are they doing here in this particular paper? They're presenting 3D objects that are augmented into a real-world data set. So I think this is the holy grail of simulation, in my opinion. And I'm going to discuss some of the work that Berkeley is doing with simulation and relate this to this paper, because what you want to have in any kind of robotics scenario, or let's talk about autonomous vehicles as a special case of robotics. What you want to have is parallelism, right? What you want to be able to do is go through many different iterations of the same scene and also iterate policies maybe, so you can have multiple iterations in multiple dimensions and then figure out a way iteratively to the best policy given the scene that you're presented. And this is one step towards that by having data augmentation. In other words, 3D objects being put, so you're driving on the road and then they put a pedestrian in front of you, they put a horse in front of you, they put a deer in front of you, that kind of thing. And then you can do that in the way Ilya R. Presented this. Again, I'm going to talk about this a bit later, but he presented this walking robot that Berkeley did using the simulation engine of NVIDIA, where you have these millions of robots, and each one is slightly different in terms of the physics that it's exposed to, and in terms of maybe also the actuators that it's exposed to. Maybe the actuators are fixed, so it's only about the physics, but you have these millions and millions of robots, and then you have a policy applied, millions of policies applied, and then the ones that survive are the ones that end up working. This is not in our podcast. It's June 21st, 2024. This is Crimdelco. This is the second installment today. For the year, we are down 3.5%. The market is up 14%. We're underperforming by 17.5%. So two papers, both presented by Sanja Fiedler. She heads the NVIDIA autonomous driving team, and also the head of AI actually at NVIDIA, which is pretty impressive. Now, let's talk about paper number one. So this is a paper that discusses grounding images with LLMs. So what's the problem here? Let's define the grounding problem. The grounding problem is you see an image and you add a label to the image and the objects in the image. That's the grounding problem. So you have an image with trees and apples and donkeys, and you want to make sure that the tree is labeled as a tree, the apple is labeled as an apple, and the donkey is labeled as a donkey. So that's what grounding means. Now, once you ground that, because of the cognitive abilities of LLMs, you do have what my friend Peter Nguyen, the author of the paper I discussed in the second episode of CVPR 24, there is knowledge, okay? There is knowledge implicit in an LLM, and that knowledge can be used maybe for semantic understanding. So this is the key idea. And in this paper, Sanja talks more about the engineering aspect of actually grounding images. So what this really means is, in a nutshell, it's first to be accurate, right? You want to be accurate. And then second, you also want to link it to the cognitive abilities of an LLM. Now, the way you improve your accuracy is actually through iterative discrimination. So you use an LLM to discriminate a VLM, video language model. This is the key idea here. And I'm very excited about this. And NVIDIA has done this before. They're using these cognitive transformer-based models, whether, let's call them LLMs for simplicity. But the idea is the same with all kinds of transformer-based models, right? You have this compressed knowledge that actually has also semantic understanding. This is the key. And with this semantic understanding, you can then do things, right? You can have a self-driving car maybe do things that a machine that doesn't have this cognitive ability might not be able to do. For example, be more careful when driving next to a school, because the image is labeled as a school, and school is in a semantic context something you should be more careful about because there's kids. So that's kind of the idea here. There is some technicalities that they discuss, such as connecting, the actual, let's say, coordinates of an object with the with the language. In other words, the vector that is attributed to the coordinates of the image, they need to be matched. So those are engineering problems that I don't want to go into here. I think the big picture message here is that NVIDIA is actively working on bringing in semantics into images and also making them more accurate. I would say this is, if you will, this is sort of auto-labeling 2.0. The next paper I want to discuss here is 3D augmentation of real drive videos. Again, the whole thing is in the context of self-driving, but you can extrapolate this, for example, to robotics, right? It's not very different. And the idea here is that you have a scene of a car driving in a road, and then you keep adding 3D obstacles to that road. That's the idea. Why is this important? Well, this allows for parallelization. And I think we at Orange Capital Partners are strong believers in the ability to use simulation and parallelization of objects and policies towards getting better trained AI agents. So the embodied AI agent, in our opinion, will be trained on simulation eventually. We're not there yet, and real-world data is still scarce or will always be scarce relative to simulation. So that's not even a question. The problem is that we're not fully ready for simulation for various reasons. So this is one step towards that solution. For example, we have the ability to actually augment a real-world data set with a real 3D image. For example, we can put a donkey in the road, and that donkey has looks real. And when I say real, I mean it has to look realistic for the robot. So whatever the robot perceives in real life has to be the same when it's augmented. I mean, it's not very different with humans, right? When we do VR or AR, we have a certain model in our brain, the way we perceive things. And the goal of VR and AR is to make those synthetic images be perceived by our brain in a similar way. So in that sense, it's the same thing. How that is done, again, those are technical questions I don't want to go into here. But fundamentally, the key is the ability to augment a picture with several scenarios. And let me just explain why this is so important. Because, and this goes to a paper that Ilya R. discussed in conjunction with Jitendra Malik, and Malik spoke about this in I think around March when he gave a presentation somewhere in Europe. I spoke about this in my Foundation Models for Embodied AI Agent series. So what they did there is they had a robot walking, and the robot walking is walking in million different environments, in parallel trained on million different environments or millions of different environments with different types of physics exposed. And I believe also with different policies. So what you can have here is you can have policy parallelism, physics parallelism. So there is this, explosion of parallelisms that can be exploited in compute. This is what makes NVIDIA so powerful, right? Because that's what they're doing. And they're using science and scientists like Sanya to push these ideas to industry. And I think this is actually a great example of also why NVIDIA is such an interesting investment, to tie this whole conversation actually to the actual purpose of our capital partners, which is to generate wealth by investing in fundamentally new concepts and engineering practices. So back to the paper. So we have this ability to parallelize a scene. This is the key. So we can have, let's say, one policy and a million different versions of the same road, or we can have a million different versions, a million different policies. Now, of course, at some point, the compute budget and so on and so forth will explode. So we have to kind of keep this in line. But the fundamental idea is, again, is through parallelism, we can have data-driven simulators that can also have data-driven learning without any priors, without any heuristics, without any cognitive input by humans. This is, in our opinion, where this is going. So to summarize, these two papers are a great example of, I think, where, in our opinion, autonomous driving is going and where robotics will be going. Just as a tangent, also, I want to just shout out to CVPR. The workshop on simulation and autonomous driving was incredibly interesting. The lineup was great. The people were great. Unfortunately, we missed Tesla there. I don't know why they're not showing up, but everybody else was there. We had NVIDIA, we had Waymo, we had Waves, we had Zoox. So there's definitely some very interesting people with different types of approaches, different types of insights, all of that, which is all great. This is what a conference should be, should look like. And I think Sanya did a good job also moderating the panel discussion. And just as a final note, I just want to bring this across again. Reward function, reward function, reward function, right? As we are approaching a data-driven approach towards robotics, which is, Tesla has paved the way, but there's a wave of more data-driven approaches coming. As we go there, we're gonna have to start thinking more seriously about reward function design. Because in most cases, we don't know what it means to drive well. We don't know what it means to have a robot doing work in a factory satisfactory. We don't know. I mean, we have a sense and we know it when we see it, but when we actually need to train a robot, whether it's through RL or something along those lines, We need to know exactly what's good and what's bad. And reward function design can also be learned. And I think this is the key message that I got from CVPR. Thank you.